break, but if I forget, just
yeah. Okay.
Tell me to.
So the sound is good.
Yeah, the sound is good. You guys can see that.
Yep.
Great.
Oh, there we are. Okay, that's fine.
Okay, so Celia, is it possible for you to force mute everybody?
Yes, I was going to say, if we're about to get started, I will do that.
Wait 1 second. It looks like,
And then you can unmute yourself.
Celia, it looks like we can allow Adrian to record. Do we want to try doing that, or do we just want to go for the usual way we record it?
If you're able to stay on, I don't know if it gets stored on his system or your system if he's the recorder.
Okay, we'll just
So I think
leave it
you
as
should I think you should be the recorder.
Okay.
That's
All right.
okay.
Just do a little stop halfway through if we could.
Yeah, you can chat if you want to remind Adrian or myself, and we can make it happen.
Okay.
So I'm going to go ahead and mute everyone, and then Adrian and Terry, you can turn yourselves back on.
Okay, so I think we have 61 people, 62. We can wait a few more minutes to see if other people are joining, or we can get started.
Let's get started, and you can say a few words and make an introduction, and then we'll be good to go, I think.
Very good. This is our second webinar for the year. This is the QED-C, the Workforce Development TAC. And it is our great pleasure to have as a guest today Dr. Terry Rudolph. He is an Australian quantum physicist who grew up in East Africa, completed his PhD in Canada, teaches at the Imperial College in London, and leads a company that's building photonic quantum computers in California. He is the R in the PBR theorem. His book, Q is for Quantum, teaches a theory that is at the forefront of modern physics, but not to an audience that you would normally associate with such a book. Instead, it's aimed at everybody. If you have a basic understanding of arithmetic, you will be able to understand the bleeding edge of quantum computing. So, ladies and gentlemen of the QED-C, here he is today as our distinguished guest. Would you please join me in welcoming Terry Rudolph?
Awesome, thank you. Thanks, Adrian. And just confirming you can still hear me, I am muted all right. Yeah, well, thanks for the invitation. As you just heard, I'm Australian, and I'm actually in Australia right now, in quarantine, locked in a hotel. It's 6 in the morning here, and they escort you from the airport, you know, the army and the police escort you. And they lock you in this room, and it's a room like many hotel rooms. It doesn't have proper lights. So I've been trying to sort of get it bright enough that I can see you. They do this sort of standard thing of only giving you lamps because they don't want you to see all the blood stains from all the people who tried to escape already. So hopefully you can see me all right. It doesn't really matter if you can't. Most of the time I'm going to be scribbling on this. And yeah, I'm really happy to have this opportunity. This is the first time I've really given a talk about giving talks about quantum mechanics, which is an interesting challenge. So I also want to start off by just throwing out a big caveat. I am not a teacher. Both of my parents were high school teachers. And what I'm going to be talking about today is, I'm basically going to be trying to make an argument that we could be teaching quantum mechanics much earlier in high school, for example. But having, lived with people who were teachers for 40 years, I know that there's nothing more annoying to teachers than academics coming in with, sort of new educational theories who don't really understand the full set of things that's entailed by actually implementing these ideas. So I'm hoping, to motivate people to think more about what it is that we could do with some of, in terms of improving and improving quantum education, what we could do, like bringing it in much earlier in people's lives. And one reason for that is, as you just heard, I recently set up a quantum computing company. And it's clear we're moving into a world in which there's going to be a need for a quantum workforce. And that quantum workforce, and the title of this of your committee is the Quantum Workforce Development Committee. And it's clear to me that that workforce needs to be non-PhD students. We really need to have the ability to create a large quantum workforce of people that don't have to go through many years of studying physics or math or computer science before they can enter that workforce. And so, the reason I think that is just that there's going to be many quantum companies, eventually many quantum computers. There's, by analogy with the world of classical computing, the classical computing workforce now, the vast majority of people do not have, a PhD in classical computer science. And you can sort of break up the classical workforce into the people who do things like software development and the people who build stuff and hardware, and almost none of them need to have a PhD. And I really feel that we should aim that in 10 to 20 years time, the same is true of the quantum workforce, that almost nobody has a PhD. So why can we do that with the classical workforce already? A lot of it's because students, young people have access to computers now. They can go, there's amazing ways of teaching classical computing, programs like Scratch, you've probably heard of. But it's also that the underlying mathematical structure can also be taught fairly early on in someone's career, and not only taught, but really motivated. It's actually possible to really get students excited about the power of classical computing. They're carrying around the classical computer in their pocket. They're basically, they can learn to program, they learn to play games, but at some level, they also appreciate the fact that a very small set of simple rules is creating this kind of unbounded world of whether it's Minecraft or whatever they're playing. And so, teaching classical, and I think we actually don't even do enough of that in high school, but teaching classical computing at the abstract level is pretty easy. Students don't need to know how a transistor works to appreciate how to program a classical computer. And you can motivate them with even deeper things. And I think that it's great to try and motivate young people by saying, there's deep questions about the philosophy of mind, for example. Is it the case that our minds run on the same Boolean logic that we can put into this, deep learning algorithm here? Or what is the difference between us and this supercomputer over there? So you can get people motivated by the questions of classical computing. And the math is not that difficult. Many of us learned in high school, basic circuit diagrams, the AND gates and OR gates and logic gates and so on. So what I hope by the end of this talk, you will appreciate is that you don't have to do very much more to also open the world of quantum computing to the students. If you take them to the point of appreciating classical computing and classical circuits and gates and boxes, it's actually not a big step to get to the world of quantum computing. And that, realizing this was a few years ago was quite amazing for me. And so I sort of want to appreciate, I want to convey that message, and hopefully I can do it in in a way that you appreciate, but if I don't, I wrote a lot more of it down in this book here, which I'll talk a little bit about it. Okay, so in terms of, teaching quantum mechanics, am I really serious that we could teach, 12-year-olds quantum mechanics, or maybe late high schoolers quantum mechanics? And one of the big problems of teaching is motivating students. And I think motivating quantum mechanics, that didn't happen before when I was plugged in. So motivating quantum mechanics, there's plenty of like cool features that I think you can talk about in some sense, and get people like, I see it in most of my teaching experiences is undergrads, but things that you can really get people to say, oh yeah, that's like a cool thing to think about. Teleportation is a classic one, but there's things like quantum cryptography, things like non-locality, and the sort of things that I'm going to talk about, which exponentially fast algorithms. And these are sort of abstract motivations for why quantum mechanics is interesting. There's also, of course, the fact that we can build really cool hardware. We can build cool stuff. So lasers rely on quantum effects. MRI relies on quantum effects. Transistors themselves. The GPS system runs on atomic clocks that wouldn't be possible without quantum effects. The thing about that hardware type of motivation is that requires learning some sort of deep physics on the application of the rules of quantum mechanics to those systems. But there's actually like a bunch of simple, more abstract stuff that you can do. So quantum theory is a little bit like Maxwell's, electromagnetism. Maxwell's equations are fairly simple, but you can spend your whole career learning how to apply them in just one limited scenario. And quantum mechanics is similar. So when I'm talking about teaching quantum mechanics, I'm really talking about teaching that kind of abstract part of quantum mechanics and some of these effects that you can get to without having to delve into how this math gets applied to individual physical systems. Okay, so these are cool features I think you can motivate quantum mechanics with. There's, the weirdness, the underpinning weirdness for this stuff. You say, what is it that, what's the kind of quantum weirdness that people have heard about? For that, you start giving a list of things like, well, there's superposition, entanglement, and observers, and collapse, things like this, uncertainty principle. Complementarity, or like wave particle duality. So the thing about this list, and this is a non-commutativity would be another one related to the uncertainty principle. The thing about this list is that these are features of quantum mechanics that are basically jargon. These are words that we'll often write down in sort of pop sci books or even in introductory quantum books. But unlike a list of sort of actual applications of quantum mechanics, this list of just words that we came up with to explain features of the theory or to sort of capture funny things that go on in quantum mechanics. And I think using these words is really detrimental to helping people understand what's going on. We want to give a quantitative understanding. If we just say things that sound cool and sound weird, that's not, we give people the impression that like, oh, they've understood something, but in fact they haven't. So I'm sort of quite passionate about teaching quantum mechanics and avoiding as much of the jargon as possible, right? Try and avoid it. In fact, in my book, Q is for quantum, the word quantum does not appear anywhere inside the book except the epilogue. It's in the title and it's in the epilogue, and I don't use the word quantum at all. Okay, so what's the barrier to teaching this weirdness? I mean, this stuff is super cool once you do understand it. But the barrier to teaching it is, of course, mathematics. And if you say, what is the kind of critical mathematics that students need to learn to get into quantum mechanics, the sort of standard list would be you need complex numbers. That states in quantum mechanics are basically vectors in Hilbert space. Evolution of physical systems, like unitary operators. In fact, all of this stuff is even more technical generalizations of them. Measurements of projection operators. So there's a lot of advanced mathematics that the vast majority of people will not be exposed to until they're well into their undergrad, before they'll get exposed to most of this stuff. Okay. So what I am going to try and outline is the procedure for teaching this kind of stuff that at least if I use jargon, I've always given a precise definition of it, so that there's like a rigorous definition of what it is, that it isn't, I want that to always be the case, that everything has a precise definition, or I just don't use it at all. But I want to not use any of this stuff. Okay. And I was surprised that this is possible. It turns out that it is. So let me sort of, this is a talk about giving talks about quantum mechanics. So let me run you through a lot faster than I would do it with some students, obviously. But roughly speaking, how I start off giving sort of quantitative explanations of weird quantum phenomena. So I start off by talking about a simple physical system, which is just a ball. Okay. And this ball it has two states. Don't use the word states because state itself is a loaded term, but I don't use it sort of, well, until I've defined it, but it has two physical properties, two configurations, which is that it can be black or white. Okay. And so, most of you know a lot of quantum mechanics. I don't really go into what those physical states are, but everything I'm going to talk about is stuff that we would be able to build one way or the other. The two states could be, a particle in one of two spatial locations. It could be up or down spin of a particle, but you could really do something very close to what I described in what follows by using two energy levels of an ion, and they look different colors when you scatter a laser off them, for example, so red or green or something like that. So that I really don't want to lie to the students. I want to talk about stuff that we really can do as much as possible. So yeah, we can create the system. It has two states, and then we can change the state. So the evolution is we want to change state. And so, for example, the simplest way changing the state of the system is going to be, you have a box with a hole in the top. I'm going to label the box not, and you take a ball that's white, and when you drop it through, the ball comes out black. Okay. So this is analogous to the NOT operation in classical computing. The classical circuits, you have a bit value 0, the NOT of the bit value is 1, or the not from Boolean logic, the negation true is false, and so on. And that's why I label it not, just to make it sort of map to other things that students may be aware about. But you could have called it flip or something like this. And the other useful concept that we can get by just thinking about this single box is that, and I'm going to stop trying to draw in 3D because my drawings are not great, but that we can concatenate boxes if we want. And drop a ball through, and then not will be a ball that comes out wide. Okay. So I think, as I was sort of alluding to at the beginning, it's quite amazing that you can teach students that a very simple set of rules to just change a binary value of some physical system can actually produce, all of the computational complexity by which I'm talking to you right now. Everything in classical computing can be brought down to some very simple rules of very simple boxes. So I go through several steps of doing this. My favorite box is the C swap box. And now what I don't do in the book, but I sort of wish I had, is I want to distinguish 3 different physical systems that all still have the binary property of being either black or white. Okay? And so I would, if I was rewriting it, which maybe I'll do one day, I would take the 3 systems to be a ball, a cube, and a pyramid, and a box that has 3 holes in the top and 3 holes in the bottom. And this is a box that when you drop the balls through, they can only go through their corresponding hole. And there's just a very simple rule, which is if the ball is blank, the colors of the cube and pyramid swap. So the C stands for control, and it's best to label the box here control, and then these we call the target. Okay. So in this case, if I drop all 3 are white and I drop them through, well, they'll just come out white. Okay. But if, for example, the ball was black and the pyramid was blank, then the rules of this box are the ball doesn't change color, but the colors of the cube and the pyramid swap. Okay. And this box is universal for classical computing. It's called the and I find that remarkable that you can process all classical information. Everything can just be brought down to this controlled swap gate. In quantum mechanics, we use this 3-bit gate because it's reversible, whereas the gates that you typically learn in classical computing, things like NAND gates or AND gates and OR gates, are not reversible. That's a technical detail, not super important. Okay, so we've now set up a situation where we have these very simple physical systems that have some binary property. We even have a way of manipulating that property, the color of them, in very simple rules, and yet we've gotten across that these rules are incredibly powerful. But we're going to add one more weird box. And this box is sort of key to the whole game. And in the book, I name it after one of my weird friends and co-founders of PsiQuantum, Pete Shadbolt. And when I'm teaching, I just have the students pick who's the weirdest person, normally the person sitting next to them, and label this box after them. Okay? But for those of you who teach quantum or maybe use the IBM Q experience, this thing is basically the Hadamard gate. Okay. But I want to get across very operationally by just describing a series of experiments why this box is weird. I don't want to just say it's weird. I want people to appreciate why it's weird by, before they look at the math, I want them to see the sort of what goes on physically, and then we look at some mathematics for how to describe it. So the thing about the peat box is that if you drop a white ball in, then you find that some of the time it comes out white, but some of the time it comes out black. So if you drop a series of white balls in, you just keep getting randomly black or white, and there's no pattern to what comes out. Okay. And similarly, if you drop a series of black balls in, they just come out randomly black or white. So the natural thing to think is that, well, you know, there's some random process of what's going on inside the box. Someone's flipping a coin and changing the color of the ball as it goes past. And we can make peat boxes for the cubes and the pyramids and so on. But the question is, how do we know that this is actually not what's happening inside the peat box? And at this point, you've set up a situation where hopefully the students can understand why this is puzzling. That if I concatenate two peat boxes, so similar to what I did with two knot boxes, okay, up here I said if I concatenate two knot boxes, a white ball comes out white. The same thing actually happens if I concatenate two peat boxes. A white ball always comes out white. Okay. And if I do the same thing, but now send in black balls, black colored balls always come out black. Okay. And, you know, this should hopefully be puzzling. And if it isn't, I spend a long time trying to make sure that everyone can understand why this is puzzling. And the reason it's puzzling is that if it's the case that a ball comes out of the first peat box, randomly black or white, and if it's the case, as we checked, that regardless of what color you put into a peat box, it comes out randomly black or white, then what you're expecting is that at this point here, you have a randomly black or white ball going into a second peat box, and so it should come out randomly black or white from the bottom. Right? That's just sort of the logical thing to expect. And that's not what happens. Okay. And we do all sorts of you know, tests to make sure the peat boxes aren't detecting each other or something. But then, you know, the natural thing to do, and this is introducing the first quantum mystery, is to say, well, I'm going to shine a light between the two peat boxes and look and see what color it is, okay, between the two peat boxes. And what you find now is that the very fact that you observe the color between the two peat boxes, you will see, like you will see, oh, the ball came out white from the first peat box. But as soon as you make that observation, the concatenation of the two boxes goes back to being randomly black or white. Okay. So this is you know, the mystery of observation in quantum mechanics. Somehow our observations of the world disturb the world. Okay. And if you use a mechanism that isn't invasive enough to tell you what the color is, if you turn the intensity of light down so much, well, then actually the concatenation of the two peat boxes will just go back to being, you know, black always goes to black and white always goes to white. Okay. So this is the sort of single, this is basically like the binary version of the double slit experiment, okay, which we often explain, but this is like a sort of, I think in some sense, simpler thing to explain. And now what I want to do is to make sure that the students can actually understand some mathematics of how, in the real world, quantum physicists calculate what will happen. Okay. And so this is where I have to do some math, but I really do not want to do math introducing any of these other kinds of, you know, mathematical objects. So I start by saying, well, when a white ball goes into the peat box, okay, whatever the way I describe it here is, somehow it has the possibility of being either white or black when I observe it, okay? Because If I just drop a white through, some of the time it comes out white, some of the time it comes out black. So I'm just going to pick some way of representing that. And I'm just going to make a list of two alternatives. And a list of the two alternatives, and I call this a MIST, just because I wanted a really separate notation for it. I draw a cloud around it. It's just a comma-separated list of the two alternatives of the colors of this form. And then, you know, we must have some rule that says, well, if I look at a MIST that has a white or a black in it, white comma black, that half the time I'll see white and half the time I'll see black. So that's going to be my mathematical rule. But what about a rule for what happens when I drop a black ball into a peat box? Well, again, I must have two alternatives, white and black, because again, half the time I'll see white and half the time I'll see black. But there needs to be some kind of difference between these two, because when I concatenate the two boxes, there's a difference in what comes out. White always comes out white from two peat boxes and black always comes out black. And the difference is that I'm going to do something which seems weird at first, and it's the sort of the only piece of the story which you just have to accept. We have tried many other ways of doing this, playing this game, of explaining what happens, and this is the only way that works. Everything that everyone comes up with is one way or the other equivalent to this. I'm going to put a negative sign, much like, you know, when I write -2, something like this. Okay, it's a label on the blackboard, and so I have a negative black form. Okay. And now I need to be able to explain what happens when I have these two peat boxes. Well, it must be the case. I must have some rule for determining what happens when I put what happens when I have like a MIST like this, of white comma black, and I drop this ball through. Now I'm dropping this this ball through where I haven't observed its colors, so it's really in this what I call misty state. What's the rule? And now you can motivate the rule pretty easily. You say, look, if you had you know, two alternative pieces of fruit, an apple and a banana, and then there's a juice machine there, and I say to you, what is the transformation the juice machine is going to do? Well, it's going to juice my apple or banana. How do you kind of represent that? It's like, well, you know, an apple evolved to become apple juice, and then separately the banana evolved to become banana juice. I don't know which of the two went in, but I should just think of it as like, these are just alternatives that go through. So the white ball going through should just do what a white ball does when it goes through a peat box, which we saw was this. Okay. And alternatively, if the ball kind of was black in some sense, then that should evolve under this rule, which is that black evolves to white comma negative black. And yeah, so, okay. So now we have like a MIST within a MIST, which is a potentially mysterious thing. Okay. But we want to follow rules of basic arithmetic as much as possible. And so if you think about rules of basic arithmetic that are things like 2 plus 3 plus, you know, 2 minus 3 with brackets around it, students learn that, oh, well, you know, under a certain set of circumstances, I can remove brackets. Here's how I do it. And so in that case, they would be able to say, well, I can remove the brackets here, and I can cancel the 3 and the minus 3. Okay. So now, you know, you really have to emphasize this point. Of course, these balls are not numbers, right? But what I want to teach is the same rules. I just want to use the same rules as basic arithmetic. So I want to say, look, exactly the same thing happens here. This is the same as a mist that has white, comma, black, comma, white, comma, negative black. And then just as the 3's cancelled out here, these cancel out, and we call that cancelling out interference. And so that takes me to a mist that only has a white ball in it. And that's why when I stick 2 peak boxes, one after the other, like this, and I only have white balls coming in, I only get white balls coming out if I don't observe. And that's the mathematical rule. And you can run through the same calculation for what happens when I put the black ball through, and you find that now it's the white balls that interfere with each other. Okay. And so we've now managed to get across a few of these jargony concepts that normally I would hate. The superposition is just the mist. Okay. The observer's collapse, we've at least given an operational view on. And so what I didn't add in my list here was interference. Like quantum interference, that we've shown is the cancelling form. Okay, so at this point you might be thinking like, well, yeah, this is a fun little game that can basically explain a single qubit phenomenon of 2 Hadamard boxes. So I think we want to pause and restart the recording, right? It's roughly halfway through. So I think this is a good time to do that.
Yeah, so Mary, do you need to stop and start again?
I do, and I will. Give me 1 second.